Welcome to my YouTube channel Raise Acad. Myself Yash Mishra, and today we will see that what is rotational kinetic energy. What are the concepts behind this rotational kinetic energy and how we will solve the questions related to it. So topic is rotational kinetic energy. Okay. So this is short topic of energy and work. And power also. Okay. So rotational kinetic energy is a form of kinetic energy, but it is there when the body is in rotational motion. So when body is performing rotational motion, then it has rotational kinetic energy, and which is half into movement of inertia. It is movement of inertia, half I into omega square. Omega is the angular velocity of particle. Okay. So suppose that there is a particle which is connected to the center and moving in this with of mass m and moving with angular velocity omega. So what is the energy associated with it? It has no potential energy and kinetic energy translational one is 0, and in this it is performing rotational. So its energy will be half into moment of inertia r mr square. So it is at the distance r. So moment of inertia from the center will be m into r square. Okay, so this is the moment of inertia I and omega square. So this is the kinetic energy or rotational kinetic energy associated with it. Okay, so the moment of inertia from this axis IO. Okay, so IO is m into r square, and kinetic energy will be, rotational kinetic energy will be half I omega square. Okay, so like this we define the rotational kinetic energy. Okay, suppose that there, take one example. So in the helix, okay, helix, it has both rotational energy, rotational kinetic energy plus translational kinetic energy. Okay, so like this particle is moving like this. So this is the translational kinetic energy and this one is the rotational kinetic energy in this helix. So total energy associated with the particle when it is performing helical motion will be half I omega square. I will be mr square. Suppose that this is the radius of the helix. So this is the radius r of the helix, and plus m into v square. V is the velocity with which it is moving upward. Okay. So these are the two types of energies, kinetic energies associated when the particle is performing a helical motion. Okay. So suppose that there is one particle. So suppose that this is the shape. Okay. This is the shape and this is circular shape. Okay, so this is the body of mass m which is sent with a velocity of v. So with how much maximum rotational angular velocity it will move in this circular path. So question is, with how much maximum rotational velocity particle will move. Okay, so it will be nothing but energy balance. Okay, we will do energy balance here. Okay, so it will be half m v square is equal to half I omega square. I is m into r square. R is radius of circular path. Okay, so half cancel. mv square is equal to m into r square into omega square. Okay, so this cancel. V square by r square under root is equals to omega. Omega is equals to v by r. So this is the omega max is equals to, this is the maximum angular velocity with which the particle will be moving. This is the maximum angular velocity with which particle will move. Okay, so suppose that, take one example, there is one rod. Okay, and it has some hole. Okay, and it has these types of curved structures. Okay, in this, so suppose that this is a type of board. Okay, which has this curved structures. Okay, and suppose that there is, and this is the hole. Okay, this is hole, and this is the particle m of mass m. Okay, and so it has a mass m, and it is being connected with the thread. Okay, so thread is connected and like this. Okay, so it is connected from a thread, and again downside, from this downside of the disc, again one particle of mass m is connected. So this whole assembly is connected from a thread. So this is mass m which is connected, and this thread is going like this. Now again mass m is connected. Okay, so this mass m will pull this mass upper mass. Okay, so so analyze the situation. So this will be having initially at the instant when this particle will be of mass m will be released exactly, which is exactly above the disk. So it will be released, so it will be having a potential energy of 0. Okay, so this will be having potential energy of 0, and this has a kinetic energy of 0. Okay, kinetic energy equal to 0. Okay, so and now it is rotating with after we will release, and the potential energy of, because baseline is this disk baseline, so 0 baseline potential energy, but when it will go down, potential energy will be negative, so decrease in potential energy will be equal to the increase in the kinetic energy of this upper mass m. Okay, so when this upper mass m will gain the rotational velocity or rotational kinetic energy, so how much it will gain? Maximum rotational kinetic energy. It will gain maximum rotational kinetic energy when this mass m will be at the maximum below. Okay, so when this height h will be maximum, then when this height h will be maximum, or this height h will be maximum, h max will be there, then the rotational kinetic energy of upper mass, suppose that this is mass m2 and this is mass m1, this is mass m2. So m1 rotational kinetic energy of m1 will be maximum. Okay. So when the potential energy of m2 will be lowest, then rotational kinetic energy of m1 will be highest. Okay. So this is the situation. When the rotational kinetic energy, it will move on the circular path. When the m2 is coming down, and it is m1 is also bound to move in the circular path. Okay. So m2 potential energy is decreasing and m1 rotational kinetic energy is increasing. So how much maximum rotational kinetic energy it will gain? So half m1. So this has mass, this m1. So half I into omega max square is equal to m2 gh. Okay. Upper has mass m1 and lower has mass m2. Okay. So this is the energy balance equation. Okay. So this is the energy balance equation, and kinetic energy is this one. Rotational kinetic energy and moment of inertia will be m1 into r square. Okay. But the moment of inertia in this case will keep on changing, because the radius of this disk will keep on changing. Okay. This disk radius is changing. Okay. So this we have to consider, that the radius of m1 particle is changing. So moment of inertia will keep on decreasing. Okay. So total moment of inertia will be calculated by integration. Okay. So an integral approach is required. Okay. So let's make one more time the diagram and we will simplify it. So suppose that this has a radius of r1, this has a radius of r2, and this has a radius of r3, and this inner one has radius of r4. So this integral approach will give us the most accurate answer. But what we will do, we will calculate these 4 moment of inertia and we will add these. Okay. On radius r1, on radius r2, on radius r3, and on radius r4. So on radius r1, what will be the moment of inertia? It will be m1 into capital R1 square. On r2, m2 into capital R2 square. m3 into capital R3 square plus m4 into capital R4 square. Okay. So this is the total moment of inertia. I net is m1 r1 square plus m2 r2 square plus m3 r3 square plus m4 r4 square. Okay. So suppose that it is given that radius keep on doing half of initial. Radius is half of initial. Suppose that, to simplify the question or to remove this, so r, then r by 2, then r by 4, then r by 8. So radius is half of initial r by 2. So m1 m and all has and the particle will be having a mass m1 only. this is m1 m1 m1. Okay, so m1 into r square plus m1 into r square by 4 plus m1 into r square by 16 plus m1 into r square by 64. Okay, so this will be there. So 64 plus 16 plus 4 plus 1. Okay, so this will be 80 plus 85. So 85 by 64 into capital R square. So this will be into m1. So this will be I net. So I net is equal to 85 by 64 into m1 into r square. Okay, so let's make the diagram one more time to analyze the situation. What was there and this. So m2gh is equal to half into I net into omega max square. Okay, so this is the height h which this mass m2 has came, and now this m1 is here with maximum angular velocity. Okay, so this is the situation which will be there. Okay, so m2gh equal to half into 85 by 64 m1 r square into omega max square. So suppose that for simplifying m1 is equals to m2 for simplification. Okay, so this cancel and this 64 into 2 128. So 128 gh upon 85 r square under root is equals to omega max. So omega max will be under root 128 gh by 85 into 1 by r. So this will be omega max. Okay, so like this we will calculate what is the omega max. Okay, so this is the approach which should be there to calculate the maximum angular velocity. Okay, so this was there for the rotational kinetic energy part. We saw some of the examples associated with it and what is the concepts with the rotational kinetic energy and how we will analyze the different types of situation. Okay, thank you.